So like we learned in chapter 5, we have learned all of the techniques that we need to know for integration and differentiation. So now in chapter 6 and then again in chapter 7, we're just applying what we know. So everything that we know comes back in these two chapters to some extent. Section 1 is called slope fields, and we've seen and worked with slope fields a few times so far. And now finally here is the official section on slope fields. On the AP exam there is typically one problem that asks you to do a slope field. It could be in the multiple choice, it could be in a free response. But there's always going to be something there. So, at the end of chapter 3 we learned about differential equations. Seems like a long time ago, and we've been working with differential equations ever since in chapters 4 and 5 when we're trying to integrate. We write dy equals something dx. That's a differential equation. A differential equation that involves x and y is an equation that involves x, y, and the derivatives of y, and this is an example of a differential equation. In order to take the derivative of this, you would have had to use implicit differentiation probably. So y prime is the same as dy over dx. Okay? Let me put that on here. This we have been writing as dy over dx. And dy over dx is the same as what? 5-letter S word. Slope. So basically what you have here is slope. This is what we're going to be dealing with in this section. When you're working with slope fields, you're graphing little tick marks that represent the slope of the function anywhere or at that particular point. So what we're going to be doing is working with equations that involve x, y, and derivatives of y. The equation above is called the differential equation. The equations and situations we learn about in this chapter involve differential equations, and some perfect examples of differential equations are radioactive decay. Remember the half-life problems from the last chapter? We're actually going to be able to build half-life equations using differential equations here. So a lot more powerful. Master Sword version of half-life. Exponential growth, bacteria in a pond, fish in a lake, things like that. Newton's law of cooling. I've talked about it a couple of times here and there. Some people believe that if you put boiling water in a freezer, it will freeze faster than cold water. Is that true? You just heard it? That's the first you've ever heard that? Oh, really? Okay. Cold water boils faster than hot water? So there's a heating principle as well that we can learn. It kind of goes along the same lines as the cooling problem that we're talking about here. And no, that's wrong. And then slope fields, which is what we're talking about in this first section right here. So what we're going to be working on is things that look like this. A function y equals f of x is considered a solution of the differential equation if the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. It's kind of a confusing way to say this example. Suppose that y double prime minus y equals 0 is our differential equation, like we're given that one. It's not always going to be that equation. It could be anything. In this particular example, we're trying to figure out if any of these three functions actually satisfy that differential equation. So to determine whether the function is a solution of the differential equation, y double prime minus y equals 0. So what we're going to do is we're taking this guy, because we're seeing if it actually satisfies the differential equation, and we're going to need to find y double prime and y, and then subtract them and see if we get 0. And if we do, then it's a solution. If we don't, then it's not. So we already have y. We need y double prime. So to get to y double prime, I need to do what? Take the derivative. Y prime equals cosine x. And then y double prime equals, that is negative sine x. Okay, so now we have y double prime and y. which means we can substitute them into this situation here and see if we get 0. So I'm going to write y double prime minus y, which is negative sine x minus sine x, which is negative 2 sine x. We're trying to see if we wind up with 0. Then it satisfies the differential equation if we get 0. Did we get 0? No. So this is not equal to 0, so y equals sine x is not a solution. And if I wanted to be totally formal, I'd write to the differential equation y double prime minus y equals 0. So all of this would be the answer. This would be the proof that shows why that is the answer. So let's try the second one. We have y equals 4e to the negative x power. I'm using the exact same differential equation here to try to decide if y equals 4e to the negative x power is a solution to that differential equation. So that means I need to find y double prime. So y prime is what? So negative, right, 4e to the negative x. And then y double prime is back to being positive 4e to the negative x. Good. Okay, so then I have y double prime minus y, which gives me 4e to the negative x minus 4e to the negative x, which is 0. So y equals 4e to the negative x is a solution to the differential equation y double prime minus y equals 0. So what do I do? Talk me through it. Mm-hmm. Mm-hmm.
But are you sure equals to
So
y equals b to the ex is a differential equation for y
good. Good. So there's your answer. Many different equations can be solutions to a differential equation, but not all. So you have to check on problems like this. So a slight extension of what we just did. Verify that y equals cx to the third is the solution to the differential equation. And now this time we have x times y prime minus 3y equals 0 as our differential equation. Then, once you've verified that it is, find a particular solution determined by the initial condition y equals 2 when x equals negative 3. So first of all, let's talk about that initial condition. It's not really an initial condition. It's more like a particular case. Like, I'm telling you that this graph goes through what? Yes. So negative 3, 2 is a part of the actual particular solution that we're looking for. So once we've found, or once we've verified that y equals cx to the third is a solution, then we'll take negative 3 comma 2 and plug it in. So to do a problem like this, now notice what's different about this one compared to the last one. There's an x involved, yeah. So that x is just going to remain x. It's not a part of what we're doing, but it stays in the differential equation. So I have x, y prime minus 3y.
So we take y prime.
We need to take y prime. So y prime equals
Bring the 3 down.
3c to the, or x squared.
So then let's throw the stuff in there.
Well, do we have to solve for x?
No?
We just-
X is x. We just let it be.
Throw x back in there, throw the
So
y in there.
this is x times,
3cx squared.
that was y prime, minus
3 times cx. And then shoot that x. Shoot 3. And all out for the
I love it when Michigan calls me. So distribute the x in. 3cx to the third minus 3cx to the third equals 0. Notice what would have happened if we said, well, 3 times a constant is still just a constant. So we're going to avoid that for now. And let it be like this. And now this does actually equal 0. So y equals cx to the third is a solution.
But even if we said that, wouldn't it still end up working because then we would just have to
Yeah, right, because then c times 3 here and c times 3 here still becomes a constant.
We gotta find a particular solution.
just
Plug in. So we have y equals cx to the third, and I'm plugging in negative 3 comma 2, so I have 2 equals c times negative 3 to the third. Negative 27, c, so therefore negative 2 over 27 equals c, which means the particular solution is y equals negative 2/27 x to the third. Okay, so here we get into slope fields finally. Solving differential equation can be best done using a slope field. And what this does is it allows you to see any particular solution that you might want. So once you get the slope field in there, you can kind of get an idea of what the graph is doing no matter what initial condition or particular ordered pair they give you. So slope fields are sometimes referred to as direction fields, just depending on the book that you're looking at or the class that you're taking. You might hear that. We are going to call them slope fields though. They offer a great visual representation of what the solution to the differential equation is doing. That's what I just said. And then if y prime equals capital F of x comma y. So all that means is y prime equals some function looking thing. It's not really a function necessarily though if it has x and y in it, but something in terms of x and y is a differential equation. Then each ordered pair can be inserted into the differential equation to find the slope at that particular ordered pair. And then you can plot that slope using a little, very tiny little tick mark that shows you what the slope is. By finding and plotting the slope at many points, you form the slope field. And then the shape of the graph kind of forms in front of you. So we're going to sketch a slope field for y prime equals x minus y for the points that I'm giving you here. This is a pretty typical AP type thing. They might give you 4 or 6 or 8 ordered pairs, maybe 9 ordered pairs, that you have to plot on a graph to generate a slope field. And then from there, use it to determine certain things. So what we want to do is just find those 3 ordered pairs. And we could find an infinite number of ordered pairs, but we just want to do these 3. So first, let me remind you of what y prime means. What is y prime? Right, it's dy over dx, which is the slope at a point. So we are going to find the slope at negative 1 comma 1. And we'll find the slope at 0 comma 1. And then the slope at 1 comma 1. So for the slope at negative 1 comma 1, I take negative 1 and I plug it in for x. I take 1 and I plug it in for y, and I get negative 2. So at negative 1, 1, right here, we have a slope that is negative 2. So I'm going to try to draw in a slope of negative 2. To do that, I'm going to come up here, because the slope of negative 2 would kind of follow that line right there. And then I'll draw in a little, if it'll let me, draw in a little mark. Take 0, 1 and plug it in. Now I plug in 0 for x and 1 for y, so I get negative 1. So at 0, 1, which is right here, I have a slope of negative 1. So I'm going to try to follow this little path right here and then draw in my mark. And I'll write a negative 1 there. And then we have at 1, 1. 1 minus 1 is 0, and that's an easy one to draw in. There we go. So for those 3 ordered pairs, there's our slope field. Now we could go through and find all of the slopes for all of the ordered pairs all the way through this entire thing right here. But thankfully, these 3 points right here were all this problem was asking for. So we're done. All right, these 3 problems are actually asking us to generate the entire slope field for the grid that you're given. Now, that's going to be how many points that we have to find on this? 16, yep. Each one of these locations is going to have some sort of slope on it. Okay. So the reason I'm doing it like this, as opposed to on the last one, is because that was like a 10 by 10 grid, and that would be let's see, so that would actually be 20 by 20. So we're talking about 400 little tick marks that we'd have to draw in there. That'd be kind of a long, detailed process. So let's go with this. We have a new differential equation here that we want to generate a slope field for, x plus y. So at each one of these ordered pairs here, because this is such a small grid, really, we can do most of this in our head probably. In fact, we can do all of this in our head because it's a very easy differential equation to look at. So if I start up here at negative 2, positive 2, what do I get? Yep, so I'm going to draw a little horizontal tick mark. And then do you want to go across or do you want to go down? Down, okay. Negative 2, positive 1. Negative 1. So we're going to try to draw in, visualize what an actual line with a slope of negative 1 would look like, and then try to draw in a slope that matches that line. And then we have at negative 2, 0, a slope of negative 2. So again, try to draw in, try to visualize that line and then draw in your ticks. At negative 2, negative 1, we get negative 3. Going to be kind of tricky to draw that one, but do your best to make it look steeper than this one. And then finally down here, negative 4. So that's really steep. It takes practice on these. So just keep in mind that you're trying to make it look steeper as you go. Okay, moving over. We are now at negative 1, positive 2. What do we get? Positive 1. So again, try to make that thing match. There we go. And then negative 1, 1 is 0. And then negative 1, 0 is negative 1. So try to make that match. And then down here, negative 2 and okay. And then down here, negative 3. So make it steep. All right, move over. We are at now 0, 2. What do we get? Yeah, positive 2. So it's getting a little bit tougher. You might, at some point, depending on the grid that you're looking at or how big the grid is, you could use a ruler or like a credit card or something to try to match up. Like if I put a ruler on here, try to make it look correct. Okay, with 0, 1, we have just 1, and then 0, 0 is 0, and then negative 0, negative 1 is negative 1, and then 0, negative 2 is negative 2. So try to make that one match up. There you go. And of course, I'm making my ticks enormous. You guys probably don't want to make them that big. That's a good size there. You're welcome. Over one more, we're at 1, 2, and we get 3. So that one actually, I'm going to try to draw in well with a ruler. So I need to go down 1, 2, 3, there we go. And then it didn't draw, so there we go. And then here we have a slope of 2. And something interesting also happens when you're using a ruler and you have a slope that's decreasing by 1 each time or increasing by 1 each time. I had to use this point right here as my reference for this line here. And then I stayed here because my next slope was 2. And then I stayed here and because my next slope was 1. And then I stayed here because my next slope was 0. And then I stayed there again because my next slope was 1, negative 1. So if you're using a ruler, sometimes it can pay off and it makes your graphing a little bit easier. Now on this last one, 2, 2, we have a slope of 4, which I can actually fit if I'm using a ruler, so I will. So I can actually get a slope of 4 on here. There we go. And then a slope of 3. I'm still using the same little reference point down here. And then the next one, slope of 2, and then a slope of 1, and then a slope of 0. Now when you complete a slope field, you'll start to see patterns form. If you look just at the patterns, not at what the shape of the graph would look like, what do you see? Yes, we have a slope of 0 following that line right there. So if I were to extend this graph out, it would be reasonable to assume that this line right here is just going to extend all the way through and have a slope of 0 no matter what as we extend. What else do you see? What? Above this part, we're increasing. So it's almost like we have a local minimum, a relative minimum, whenever our graph touches this portion here. What else do you see? This one right here? Yeah. It's like if we had, if we were to draw in, if we had an initial condition that put us directly on, like this ordered pair right here, we'd wind up with just this line, because we will never branch away from it. But if we're slightly above this line, can you see how we would wind up curling away? Or if we're slightly below this line, can you see how we would wind up curling away? So this line right here is actually dividing this graph into 2 distinct features, the upper portion and the lower portion. And that's what a slope field will do for you. Can we call that an asymptote? In this direction, yes. Over here, no. We don't know what goes on. Probably this just continues down forever like a parabola would. Or it continues up this way forever like a parabola would. But over here, the graph is going to approach this line and then never cross it. So talk me through the next one. What should we do? Right, we don't have a y involved like we did on this one. So for this, the only thing we need to worry about is x coordinates. So plug in -2 for x and we get -2. Now that's -2 here, but what else? It's -2 everywhere along here. So I'm going to draw in that -2 here, and here, and here, and here. Now what? Okay, -1, and our slope is -1. So draw in a slope of -1 each time. And then 0, so that one's horizontal, all the way through. And then +1 all the way through. and finally positive 2 all the way through. So what shape of a graph is this one? It's a parabola, yeah. If I were to pick an initial point like right here, you can kind of see how this would curve around in the shape of a parabola. And that's right, that should make sense because really this is dy over dx, which means I can rewrite this as dy equals x dx. And if I integrate that, then I wind up with y equals 1/2 x squared plus some constant. And that constant in this case is going to be the y-intercept. So if I say that my c is like -2, then here I am down here, and then I would draw in a parabola that has a dilation of 1/2 on it, and I'm going to wind up with a shape that looks like that. So this is stuff really you've been working with all along. It's just a different way of looking at it. How about this one? Just the y-coordinates. So where do you want to start? Start at 0. What do we get? 0. So when y is 0, we get a slope of 0. So hopefully you thought of a horizontal line. When y is 0, we get a slope of 0. If we go up to 1, we get a slope of 1. So slope of 1, and that's for every y-coordinate. That's 1. Up to 2, positive 2. Down to -1, a slope of -1. Down to -2, a slope of -2. So what kind of graph is this? Actually, it's not a sideways parabola. If it was, then these slopes would be getting less and less as we go along. We are doing this, or we're doing this. What is that? So what kind of graph do we know of that will come down and get close to but never touch the x-axis? It's an exponential, yeah. If you were to rewrite this, this would be dy equals y dx. If I divide both sides by y to get y on the other side, I have 1 over y dy equals 1 dx. What happens now? Yeah, this is y prime over y right here. So we would integrate and then eventually move that over. You wind up with an exponential looking function. So that's how you do a slope field. On the AP exam, if you have to generate one, it's going to look mostly like this. They'll give you a small grid where you have to find several points. And these, we did 16 of them, and they were easy to come up with. On theirs, they might give you 8. Okay? But that's the idea. Okay, so I've given you all of the ordered pairs in a table format. This is exactly what we were just doing, except this time, rather than doing it in our head, it's all written out here. That's the only difference. And the reason I'm doing that is because these numbers get kind of big and the pattern isn't exactly obvious. So we're going to go through this one and come up with this graph. But then, sketching a solution using a slope field involves the slope field as well as some known conditions. Sketch the field first, then apply the condition to sketch the graph. It's helpful to make a table of values, so I gave you the table of values. So we want to sketch a slope field for this guy. Then sketch a solution that passes through the point 1, 1. So let's worry about the slope field first, and then we'll try to sketch in that general solution. Or the particular solution, sorry. So if I have -2, -2, I'm starting out all the way down here at the bottom. What do I get for -2, -2? -6. And what do I get for -2, -1? -5. And what do I get for -2, 0? -4. So the next one will be, and the next one is, and the next one is. Okay, don't get so wrapped up in a pattern that you go too far. Notice that we've gone through all the negative 2's here. Now we're switching to when x is negative 1. So we've taken out this whole column. Now we're going here. When x is negative 1 and y is negative 2, what do we get? Negative 4. And then? Negative 3. And then? Negative 2. Negative 1. And 0. And the next one? Okay, we're at negative 2 now, that's right. And then? Yep. Okay. 1, 2. Good. And then here, when x is 1 and y is negative 2. Okay. 1. Yep. Yep. Okay. Now when x is 2, we get, and then. Good. So there are patterns that appear, just don't get so carried away in the pattern that you lose track of what you're doing, okay? Be careful. So now we have all of those ordered pairs, and we have all of the slopes of those ordered pairs, so we're going to try to carefully sketch those in. Try the best you can with this negative 6, negative 5, negative 4. Try to make them look steeper than the one before them, or the one after them. Okay, so negative 2, we have a slope of negative 6. That is pretty much vertical. And then slightly less vertical, slightly less vertical, slightly less vertical, and negative 2, positive 2 has a slope of negative 2. I can actually draw that one in there. There we go. For the next one, we have negative 1, negative 2, which is down here, a slope of negative 4, which actually fits. We can go all the way up here and get that on there. And then there, and like that, and then slope of negative 1, and then a slope of 0. So always watch for little reference points that you can use to draw on these graphs. All right, so now we're at 0, negative 2, which is negative 2, and then negative 1, and then 0, and then positive 1, and then positive 2. Now for positive 1, negative 2, we have the 0, and then 1, 2, 3, 4. Finally, positive 2, negative 2 has a slope of 2. That's going to be tough to draw. And then 3, make it steeper, make it steep, steeper yet, very steep. There you go. There's a couple of things that when you graph a particular solution, you're going to really want to pay attention to. I'm going to pick a slightly different color here. So notice that we do have some horizontal here. But it's not a horizontal all the way through. You don't always see it. But if you look, you can see that it's kind of following along this line right here. Okay? I don't want you to draw that in there. I want you to see that it's following along that line. So when you draw in a particular solution, you better be horizontal as you cross that little imaginary dotted line that I just drew in there. If this is an AP exam and they're asking you to draw a particular solution, that's what they're going to be looking for. Did you go horizontal as you crossed over that line? Probably as a grader, they'll take a little ruler and put that ruler on that line to see if that graph is horizontal there. So you want to be careful about that. Also, these negative 1 slopes and these positive 1 slopes in here, you'll want to make sure that you are as close as possible to that particular slope there. The rest of it, ballpark. But here, for sure, you got to be horizontal there. Okay, now they want through the point 1, 1. So 1, 1 is sitting right here. Also notice watch for places where the graph will never cross. Like we had, let me go back real quick. We had here, this line, the graph will never cross that. So watch out for places like that here. Do we have any of those here? Actually, we do. this slope of, where is it? See how everything's kind of tending towards a little, it's almost like a vacuum sitting over here sucking all of the graph in this direction. So make sure that your graph is kind of winding up over here if you wind up doing that. Now this is not an asymptote here. We are going to cross that. This is just where our graph has to go horizontal. So try to visualize what that thing's going to look like. Now if we come down here with a slope of 1, we must be sort of curving around somehow and then coming back up this way. And we must be kind of taking off in this direction here. So just try to picture what that thing's going to look like. You don't necessarily have to go all the way down to here. Or you might go below it, or you might come up above it. Probably more likely we're kind of swooping around just above that 0 right there and then coming this way. But whatever you do, make sure that you're horizontal there. So I'm just going to try to draw in a curve that sort of matches what we're looking at. That seems pretty reasonable right there. Is it a parabola? No, it's not. This thing is kind of getting pulled in this direction, whereas this side kind of is looking sort of like a parabola. So be careful, it's not a parabola. And hopefully my graph doesn't look like one. But hopefully we are horizontal here, and if you draw a line through there, you curve through there, and it doesn't look horizontal, you'll want to fix that. But that's how you do this. This goes to the point 1, 1. This is the slope field for this differential equation right here. So we have satisfied the 2 requirements of the problem. I should have gone through that ordered pair though. Okay? Hopefully it doesn't look that sloppy.